So let's begin by doing a couple problems here. Sometimes you don't have a perfect cube that's obvious to you. Like if you look at your cube numbers, we're looking at 1. I better make sure I do a color you guys can see better. 1 is a cube number. 8 is a cube number. 27 is a cube number. 64, 125. The next cube number after that would be 6 cubed, which is 216. The next one is 7 cubed, which is 343. So when you're looking at this number here, you might be saying, well, gee, I don't see any of these cube numbers here. But remember, you can write this as a factor of two numbers. So if you check carefully on your calculator, you can find out that 27 is a factor. So this is 27 times 5, for example. So the advantage of writing it this way, or the advantage of knowing this little fact, is that we could write this as the cube root of 27 times the cube root of 5. Now this one we could simplify. Because that's a perfect cube, we could rewrite that one as the cube root of 3 cubed times the cube root of 5. Well, remember, an exponent cancels its root, so that cancels off, so we get 3. Now this, nothing cancels, so we could then write this portion as the cube root. We put a little 3 in there to remind us that it's a cube root, and we put 5 right here. Okay. And so this is what we mean by write the expression in simplest form. What that means is that there should be no perfect cubes that can simplify and come out of there. And so we've removed the one that was in here, and now it's on the outside of the radical. Okay? So simplify means if there's any perfect squares or perfect cubes or perfect fourth roots or whatever, you pull those out because they cancel off. Just like right here. Okay, so let's continue, and then we have this one here, and let me I would like to show this one a little bit slower. So we had the fifth root of 7. It was? I think it was a fifth root. Oh yeah, fifth root. Okay, so fifth root of 7 over the fifth root of 8. Well, what we were talking about yesterday, and we just kind of got started on it, is it's considered bad manners or bad mathematics to have radicals in the denominator. So the question is, what should we multiply by to get a perfect fifth power number here so that it could cancel off the fifth root? We want something inside of here to the fifth power, you see? So then that exponent can cancel off the root. That's the idea, you see? So you got to think a little bit. Well, first of all, I realized that this number is a perfect cube. That's 2 times 2 times 2. So what I have so far down in this denominator is I have 2 cubed. Well, this is a fifth root, so the cube does not cancel off a fifth root. But if I were to get 2 more 2's in here, then it would cancel that off. Are you guys done? Thank you. Well, it's kind of annoying when people are talking around. Okay, so that gives me the plan then. What I want to do right here, what I want to do is get 2 more 2's in there. So I'm going to put a 2 squared. Because this one already is a 2 cubed, you see? And so what I'm going to do is I'm going to multiply by a 2 squared here. And of course a 2 squared is actually 4, right? So what I can do is rewrite this one as 4. And if you want, I could have rewritten this one as 4. But I think what I'll do is I'll leave it the way it is at the moment. And so I have this now as the fifth root, and 7 times 4 is 28, and I don't see anything that will cancel off out of there, so I'll just leave the numerator alone. But now what I have down in the denominator is a fifth root of 2 to the fifth power. And now the exponent cancels off its fifth root. And so we got rid of this radical in the denominator. We have the fifth root of 28 over 2. Okay? Now, I know some of you guys might be thinking, why can't we take this 2 and cancel off that and make a 14? Right? Some of you guys are thinking that? You can't do that. Okay, so why? Well, let's back up just a few little steps here, and I'd like to explain why. Okay? One of the properties we have about radicals is that you can split up. For example, if you have a fifth root and you have a over b, you can split this up into a fifth root of a divided by a fifth root of b. But notice the index is the same. You can do this property when you have an index of 5. You have to keep the index 5 here, and you have to keep the index 5 here. But notice right down here, this 2 does not have a fifth root right here. And so you cannot go back this way and then cancel them. Does that make sense? You can only combine them if they have the same index and stuff like that. In fact, what would the exponent be on this 2? If you were to write an exponent on the 2, what would it be? It would be 2 to the 1. You see? That's a fifth root. This is an exponent of 1. So it's kind of like they're not like terms, so you can't cancel them then.
So say if they were like terms?
Yeah, if you had a fifth root here, then you can combine them into 1 and then do the canceling inside the radical. You see?
So when you leave it as the fifth root of 14?
No, you can't do the fifth root of 14. Well, in that case, at this, yeah.
It would be that.
Yeah. Okay, so anyhow, please be aware of, it's easy to make mistakes and they're natural ideas. I mean, most people look, well, why can't we do that? They're dividing, right? Well, this has a fifth root on it. This one does not have a fifth root, so hopefully that you'll catch that. Okay, so these can be kind of tricky. Okay, so we need to do a few more problems, and then, like I said, we'll get back to our study guide. Okay, how about this one? Once again, I don't notice any perfect cubes. The perfect cubes would be like 1. I'm going to switch colors. 1. What's the next one? 8. The next one? 27. The next one? 64. 125. Yeah, we're doing cube numbers here. 216. And 343. Okay, so those are perfect cubes, and you look up here, and you're probably thinking, well, gee, hi, how are you? I don't see any perfect cubes up here. So you're looking here, 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 and you're going, well, now what? Well, you need to search for one. There might be a factor in there. And so usually what I do is I make a guess. If you're looking at this list of numbers, what would you guess is a factor of 104? 8. That's my guess too. I would just say, okay, 8 times what number gives me 104? And so now you just use your calculator. And what is it? Is it 13? Okay, so according to my friend Noel, he says it's 13. So we could then write this as 104. We could rewrite as 8 times 13. Well, the advantage of doing this is that I could simplify things a little bit. So now I could write this as a cube root of 2 cubed, which is how we write the 8, right, times the cube root of 13. And as you might imagine, This is a cube root, and the exponent is a 3, so they cancel. So we get a 2 here. And this one does not simplify any further. So we can write this as the cube root of 13. And there you have it. That's how we simplify some of these. You're going to have to be familiar with some of these cube numbers. You'll probably also have to be familiar with some of the fourth powers, like n to the fourth power. This is n cubed, right? Okay, so let's go now. What I want to do now is let's go to our study guide for a little bit and do a couple of those problems. So yesterday, I think we just wrapped up number 10. Okay. We're just finishing number 10. Okay, so now let's talk briefly about numbers 11 and 12. Okay, do you see this here? We have, I'm going to write it a little bit larger here, 3 times 6 to the 1/4 power plus 5 times 6 to the 1/4 power. Now, I want you to compare that real quick to this equation, okay? 3x squared plus 5x squared. Hopefully, if you're doing this problem, you would say quickly, what's the answer? 8x squared, right? Now, do you see the comparison here? These are like terms. You have, instead of x squared, you have a 1/4 power. And you have 1/4 power here. If you have two bases with the same exponents, you see the exponents are the same, and you have the bases are the same, then you can add them just like we added here. And so if you have 3 of them plus 5 of them, you get 8 of them, right? So now you have 8 times 6 to the 1/4 power. Does that sort of make sense? Can you recognize that? Okay, can you take 5 seconds to do number 12 then? Please tell me you're done already.
Does it matter there in parentheses?
Well,
As long as they're the same.
it's the same number to the same exponent, right? So you have 954 to the 1/2 power minus 54 to the 1/2 power. Well, aren't these the same? Aren't these the same? Well, then they add just like these x's do. And so you got 9 of them. You subtract 1 of them, right? And so now we would have 854 to the 1/2 power. Now, hold up just a second. We might be done, but can we simplify anything inside of here? Is there anything inside there that can come out of there? 54. Now we're looking for perfect squares, not cubes. Are there any perfect squares? Because remember, a half would cancel off a perfect square. Wasn't it 9 times 6? Isn't 9 a perfect square? Let's look at the perfect squares. We're looking at 1, 4, 9, right? 16, 25, 36, then what? 49, 64, 81. You see any perfect squares in here? Well, I do. Isn't this equal to 8 times 9 times 6 to the 1/2 power? And then, can't I replace this number and rewrite that one as 3 squared times 6 to 1/2? Okay, I'm taking multiple steps here, but normally a few of these steps I just do in my head. And I'm showing you for the sake of simplicity here. Some people don't see these steps, this step here. Now, if I multiply the exponents, I get 8 times 3 squared. Now that is being multiplied by this 1/2, okay? And then we have 6 multiplied to the 1/2 power. And of course, on this 3 here, this cancels off with that 2 there. So I get 8 times 3. Now I get 24. And then I have 6 to the 1/2 power. Now granted, I took about 5 steps here, and some of you guys could have gone from this to here immediately. Does that make sense? Okay, so that one simplified a little bit further. Now, this answer would have probably been okay, probably. I mean, depends on what the directions were. This is also an equivalent answer. Why do you need to know this? Well, sometimes when you take state test, maybe this is one of your answers and it's multiple choice. They didn't write the answer like this. You need to realize that, hey, wait, if I continue to tinker with this, I could rewrite it this way. You see, the problem is that they might have answer D that says none of the above. None of the above. And if that is where you're limited, you would have thought that's the answer because you didn't see. Does that make sense? So you've got to be kind of prepared for various ways of representing things. Anyhow, that's kind of unfortunate. But there's 11 and 12, right? Let's move on. Can we move on to the next page? Okay, this is our last group on the study guide. And what I think we should do now is 13, 14, and 15. And I think you can simplify those. And then we'll talk about the last remaining ones, okay? So I'm going to pause the video. Okay, let's go over a couple more of these harder problems, I think, on the study guide. This one, for example, we get, by the way, if you haven't tried this yet, just go ahead and pause the video and then try it first, and then see if you get the same result I get. What we have on number 18 is the 4th root of 81 m to the 4th 16 n to the 8th. Now, you know that things to the 4th power will cancel off the 4th root. So the plan here is to rewrite as much as possible the factors in here as perfect numbers to a 4th power. And so we could rewrite this, for example, I recognize that one as 3 to the 4th because that's equal to 3 times 3, which is 9, times 3, which is 27, times 3, which is 81. So how about if we rewrite this as 4, and we could write this as 3 to the 4th power. M is already to the 4th power, so that's kind of nice. M to the 4th power. And down here in the denominator, well, first of all, what we could do is separate things out. We could write this as a 4th power down here as well. And we could write this 8. Now I notice this is 2 to the 4th. And that's because 2 times 2 is 4, times 2 again is 8, times 2 again is 16. So this is 2 to the 4th power. And now, this is already a perfect 4th power, but let's rewrite it as n squared to the 4th power. You see? Like that. Because you'd multiply exponents, and so you get 8. Okay, so from here, these exponents here that we have that are to the 4th power will all cancel out the 4th root. So this becomes 3 because this one would cancel that one off. And this would become m because this exponent cancels off the root. So in the numerator we'd have 3 times n. Now similar fashion, the 4 would cancel off here, give me a 2. And the 4th power would cancel off here, giving me an n squared. Now some of you guys are going to be able to start with this expression right here and go to here immediately. And it might take a little while to get good at that, but eventually, hopefully, you'll get to that stage. And so that's how we could simplify number 18. Let's look at number 15 because that one is a bit difficult. You kind of look at it and you go, looks kind of simplified already. And our task is to simplify it. You're probably saying, well, gee, number 15 looks like it's simplified already. I mean, it's. But one property we can use, for example, with this cube root here, and all roots, if we have a quotient like a over b, we can then rewrite this as the square root of a over the square root of b. Okay, so we're allowed to do that. Then, as we saw earlier in the lesson and in previous chapters, we decided that we had to get rid of any square roots or cube roots or fourth roots in the denominator. And I suspect that's what we're supposed to do here. So let's go down that path and see where it takes us. So I'm going to rewrite this a little bit larger. I'm going to separate this, okay. Number 15, I can use the quotient property that says this is equal to the cube root of 2x, okay, over the cube root of 3y squared. Okay, now when I'm considering the numerator, I don't see any perfect cubes up here to simplify. My guess is that they'll probably stay the same here. But notice this denominator here. We want to get rid of the cube root in the denominator. And it's too bad that this is not a 3, because if this were a 3, it would cancel off, right? And so that kind of gives you the clue what to do here. It's not a 3, so how could we make it a 3? Well, we could make it a 3 by doing this. Let's erase these equal signs. Let's do this. Let's make it a 3 by multiplying by one more of these. I'm going to put a 3y here, you see. And in order to do this, I need to do the same thing in the numerator. And now notice what would happen. I would have, in this case, in the numerator, I could combine these two together because I have the same index, okay? And so I could use the product rule here of these radicals. And I get a cube root, and I get 4xy. And then down here in the denominator, I have a cube root, and there's 3 of these now. Since there's 3 of these, I got 3y, the quantity, cubed. And that was my plan in the first place. I can now cancel off this cube with that cube root. And so this whole thing is going to be equal to the cube root of 4xy, okay, over 3y. You see? And in my own opinion here, this probably isn't a whole lot more simplified than what we originally had, but that is sort of what we want to do on this problem, is go to there. It's called rationalizing the denominator. And the denominator, we're not supposed to have radicals in there. So this process is called rationalizing the denominator. So now you can see there's no radical in the denominator. Okay, that being said, number 16 should be easy. Number 17 should be easy. Keep in mind the idea here on those, if you had 3x squared plus 5x squared, you should all know how to do that, right? You get 8x squared. Well, why could we do this? Well, because these variables are the same and the exponents are the same. And when the variables are the same and the exponents are the same, we say that they are like terms. And so we can add like terms and we could subtract like terms. Well, you'll notice on these that the square roots are the same, the variables are the same, so you can add and subtract them. If you take a look here, these are the same, so you can add and subtract them. So 16 and 17, they're just like normal addition problems. They're like regular like term problems. So that should take only 5 seconds each for those. The last tricky problem is 18, and this one's kind of annoying. So let me raise some room here and we'll work that one out. It'd be a good idea to pause the video and try it on your own first. Maybe see if you could simplify that one on your own. But keep in mind, like I've been saying, you cannot add these two because they're not the same. They're not the same, at least yet. And so that's the clue, though. These aren't the same. I mean, they have the same index. The index right here is a square root, so the index would be a 2. And the index here would be a 2 also. So that portion is okay. But what's not okay is the inside portion. This is 5y to the fourth, and that's 20y squared. Now, if they were the same, we can add them like we did on 16 and 17. But they're not the same. So you might try some simplification. Hopefully, after simplifying things a little bit, they might turn out to be the same. Well, since these are square roots, what we'd like to do to simplify it is to find perfect squares. So let me rewrite this up here so we can see it a little bit better. We have 3 times the square root of 5y to the fourth power minus y 20y squared. Now when you examine the radicand under this square root here, I can see quickly that 5 is not a perfect square. Oh, but y to the fourth power is a perfect square. I could rewrite this as 3 times the square root of 5 times the square root of y squared, that quantity, squared. See that there? It's to the fourth power here. So it's a perfect square. It's y squared squared. And then I could say minus y. And at the same time, I'm looking for some perfect squares here. Oh, well, there's a perfect square. And notice that 20 has 2 factors in it, one of which would be a perfect square, because it's 4 times 5, right? Well, I could rewrite the 4 as 2 squared. And then I could write square root of 5. And then I could write this as the square root of y squared. Well, again, simplifying this now, the exponent will cancel off a square root if it's a square. And so I could rewrite this one as 3. Now this square here is going to cancel off the square root. So I have 3y squared because of that one. And then this square root 5 can tag along. Okay. That one did not simplify. So I'm going to leave it. And then over here, what do we have? We have a minus sign. We have a y. And this cancels off its square root. So I'm going to gain a 2 in here. This square root cancels off this square. And so I get an extra y. And again, this 5 does not simplify. So it kind of tags along square root of 5. And now hopefully you can see what the final steps here would be. I'm just going to clean this up a little bit. And whoops. Well, what did I do now? Well, we're simplifying this one. And so what we had here, I was trying to minimize that. What we had here is this was 3y squared times the square root of 5. And then we had minus y. And then we had times 2. And then we had another y here times the square root of 5. And so I just need to clean this up. Well, these two, of course, will multiply together. And so this is 3y squared square root of 5 minus 2. Now let's combine the y's. We'd have 2y squared square root of 5. And now if you examine this portion and this portion, they are the same now. And now that they are the same, we can add these two as if they were like terms. And in fact, they are like terms. So 3 of these minus 2 of these would be 1 of these. And then we have a y squared square root of 5. And of course, this looks kind of awkward having a 1 sitting out here. So we're going to kind of erase that. And then just leave it like this. And there you have it. Number 18. Kind of annoying problem. But that's the nature of some of these problems. So I think that's it. Now we should be able to finish off the study guide, and then like I said, tomorrow we'll work on the book assignment in class. So we'll stop right here.